Hey guys, today I'm going to be teaching you about forces and free body diagrams. This is going to be our first lesson in our new forces unit that we're going to be working on for quite a while. The first thing you have to know is what a force is. A force is simply a push or pull. Okay, anything that's pushing or pulling on something else. And there are two categories of forces, and every force we work with is going to fall into one of these two categories. We've got field forces and contact forces. Okay, so field forces are very weird. It's perfect that they fall into the October unit because they can act at a distance, almost kind of like magic or in Star Wars, you know. You have Darth Vader can chokehold people from across the room. Field forces can act over a distance. The flip side of that is contact forces. Contact forces must be touching the object in order to act. Okay, so field forces, they don't have to be touching. They can be far away and still have an effect, but contact forces have to literally be touching the object in order to have an effect. So we're going to look at some examples of forces down here and categorize them into field and contact. The first one is gravity. So gravity can act at a distance. For example, you've got the moon orbits the Earth because of the Earth's gravity, and the moon is not touching the Earth. That is at a distance. Or if you jump up a couple of feet in the air, first of all, that's an impressive vertical. But if you jump up in the air and you're no longer touching the Earth, gravity still has an effect. So that makes it a field force. We're also going to need to know the symbols for each of our forces because we're going to be drawing some diagrams with them, a little definition, and the direction that they can go. So the symbol for gravity that we're going to be using is F for force. All of these things are going to have F for force, and it's going to have a subscript capital G for gravity. So that's the force of gravity. And the description here is that gravity is an attractive force. Gravity always attracts. It's an attractive force between two masses. Just put an extra hump on my M. It's going to be fine. So it's an attractive force between two masses. So for example, you have mass. The Earth has mass. So there's an attractive force between the two of you. That's what we call gravity that holds us to the Earth. But actually it passes back and forth between each object. So you are attracted by the Earth, but the Earth is also attracted by you. Which is pretty cool. And the direction that we're going to be using for that is going to be down because in the context of our questions, we're going to be working with stuff that's on the Earth, and gravity of the Earth is going to be pulling towards the center, which is what we perceive as down. But in larger contexts like the solar system or planets in the sun, that kind of stuff, it's always going to pull towards the center of the object. But for us, that's the Earth and that's down. Next up, we have the normal force, which is a little bit harder to explain. So the normal force is a force from a surface. For example, you're sitting on a chair right now, and that's what keeps you from falling down to the Earth. Okay? Gravity's pulling you down. The thing that's holding you up is your chair. So to counteract the force of gravity, the normal force offers a force going up. And that's what we call the normal force. Now, the chair can't do anything for you if you're not sitting on it. So that makes it a contact force. You have to be in contact with the chair in order to feel that normal force. The symbol that we're going to use for it is capital F with a subscript capital N for normal. So that's force of normal. And the description is going to be any supportive force from a surface. Any supportive force from a surface. So that could be the chair, the floor, the ground, anything like that. Now the direction in the example I just gave you is that it's going up. Now the reason for that is because your chair is horizontal, so the force goes up. And that's at a right angle to each other. So really the normal force is always going to be perpendicular to the surface. Perpendicular to surface. All right, so if you've got a ramp, because we're going to be doing that later on in the unit, the normal force goes perpendicular to that surface, which means it's slanted. Our next force is a little bit easier. That one's tension. Tension comes from a rope or a chain or something that's pulling And it has to be attached to the object. A rope's going to do you no good if it's over here and your object's over there. So it has to be contact. We call that one F with a subscript T. The description for that is a pull, because you can't push with a rope or chain, a pull from a rope, chain, etc. Because there's lots of options for that. You can do string, you could do thread. Anything of that nature is going to be tension. And the direction, it can go any direction. You can pull up, you can pull down, you can pull to the side, pull at an angle. Any of those is perfectly fine. Next up is friction. Friction you should know about. It is a force that resists motion. We can go ahead and put that in the description. It's a force that resists motion. And it usually comes from sliding or rubbing. So resists motion of something sliding is what we'll put. Sorry, my handwriting's not the best here. Force that resists the motion of something sliding. Okay, so you can't have friction unless you're sliding across a surface, so it has to be contact. You can't have friction without the contact. The symbol for that is going to be a capital F, and this one's a little bit different, breaks the pattern. It is a lowercase f for the subscript to differentiate from the capital F for force. And friction can technically go any direction, but it is specific to the motion. It always goes opposite of the motion. Always opposite of the motion. So if you're sliding a box to the right, friction's going to the left. If you are pushing something up a wall, friction's pushing down. Okay, it's always opposite of the motion. Not necessarily opposite of your force, but opposite of the motion. Next up, we've got the force applied. Now, this is any force that you provide. Any force that you provide, which is kind of a wide umbrella of stuff. Like if you literally walk up to something and push it, that's applied. If you press the gas pedal in your car, that's a force applied. Okay, it's a very general, very broad category. It covers a lot of stuff, and it is F with a capital A. But we all know that this is unfortunately not the universe of Star Wars. That is a galaxy far, far away. So we do not have the force here, which means our force applied can never be a field force. Instead, our force applied has to be contact. You have to walk up to something. You can't do it from across the room. So that's a contact force for the force applied. And that can go any direction. Okay, next up we've got the magnetic force. The magnetic force, which is one of my all-time favorites, is a field force. This is any force or forces between two magnets. And there are some other things that go along with that, but you have to take my AP2 class if you want to learn about them. We call that one F, and this also breaks pattern, with a capital B. The reason for that is because the magnetic field is called the B field. I don't know why they call it the B field, but that's why we call the subscript there FB. And that can go any direction. We've also got electric forces, which are between two charges. Forces or force between two electric charges. The direction for that is any. The symbol for that is F with capital E. And electric forces can go over a distance, and that is a field force for that reason. Okay, so those are all the types of forces that we could encounter in this class. There are a few other forces in existence that we won't go into, but this is not an exhaustive list. It's just the ones that we're going to use. Now today we're going to be learning a lot about representing forces with some diagrams. So when we do that, we have to remember that forces are vectors. Okay, so forces are vectors. We learned about vectors 2 units ago and used them a little bit last year. You remember our Despicable Me villain. You had Vector, who is committing crimes with both direction and magnitude. Oh yeah. So the forces have both direction, which is going to be where our arrow that we use is pointing, and also the magnitude. So that's where we look at the length of the arrow. So anytime we have a force, like say I want to push something to the right, we would represent that as an arrow. This would be my force applied. Because it's going to the right, that's the direction. And based on how long it is, that's going to represent the length. So this would be a hard push. This one down here that's shorter would be a softer, gentler push. So we're just going to be using arrows to draw those. And then we also need to know the unit. The unit is named after my dude, Sir Isaac, whose last name happens to be Newton. So the unit for force is going to be the Newton. And now we're going to flip over to the back and do a couple of examples. Y'all work on some practice and we'll be good. Okay, so the actual skill that you need to be able to do today is draw a free body diagram. And here's the 5 steps. They're written on your paper for you, but I am going to walk you through them on this example down here. It says a car accelerates on a road with friction present. We're going to draw a free body diagram showing the forces present on the car. So in order to draw a free body diagram, we have got to follow these steps. Step 1 is draw a coordinate system. So that's exactly like in math. You've got your x-axis and your y-axis. That's a coordinate system. Okay, there's other types, but this is the one that we're working with. And I'm going to assume that you guys want to keep our typical positives and negatives with this. So we'll have positive being up and to the right, negative being down and to the left. But you can choose your positives and negatives just like we did in our previous units. Most people choose the conventional. So that's step 1. Step 2 is going to be to draw your object on there. I can't draw, so I'm drawing a little dot. If you want to draw a full-blown car, because that's what we're working with, you can. But it's way less time-consuming if you just draw the dot. And the next thing you got to do is think. You got to use your brain. Think about what forces exist on this car that's accelerating down a road where there is friction. Okay? So I want y'all to pause the video, talk out loud, look at your list on front, think of the forces that are there. There's going to be 4 of them. Try to figure it out on your own, which 4 exist, and then play the video again, and I'll help you, or I'll show you if you're right. So pause the video now. And welcome back. So hopefully you guys got the correct 4 forces. They are gravity going down. So how we'll draw that is you do an arrow and you label it the force of gravity. Force of gravity goes down. Now we also had, since the car is not falling through the road into the center of the earth, we have the normal force going up. That's the force from a surface. That's the normal force. We got force of gravity, normal force. Now those 2 arrows should be roughly equal because your car is not falling down to the earth. It's also not flying up because the road booted it, okay? It is traveling exactly at its same height the whole time. So your normal force and your force of gravity should be balanced. Now, next up, you got to have a force applied to make your car go. So you got force applied. I'm going to assume y'all picked to the right, if y'all picked at all, but I'm going to put it going to the right in the positive direction. And then against that, we have friction. If our car is going to the right and there is friction present, sorry, that means that friction has to be going to the left. Now I'm going to make my friction arrow smaller than my force applied arrow. Why? Because it says my car accelerates. In order for my car to accelerate, my applied force has to be bigger than my force of friction so that the total force is going to be going to the right, which is a concept we'll be developing over several days. But this is what your free body diagram should look like. You simply have a coordinate system. You pick the forces that you think are on the object and you draw them and label them as so. Now next up, we got to talk about the net force. Now you can't really do your net force effectively without your diagram. So you always have to do your diagram first. But the net force is going to be looking at the sum, S-U-M, of all the forces on the object. Okay, the sum in math, means adding everything up. So when we do that, we're going to represent it with the Greek letter sigma. This is a sigma. It looks kind of like a weird E. You can also do it looking more like a backwards 3. I've seen it both ways. Okay, but that's the Greek letter sigma. It means sum. If you've taken statistics, you've seen it a lot. So what that means is you're going to sum or add all of the forces. But we're going to treat our directions separately, just like we've been doing in previous units. So you're going to sum the horizontal forces and the vertical forces separately. We'll do the horizontal in one and the vertical. We'll see what that looks like down here. I'm going to try to not lose my diagram so that I can still refer to it. Okay, so the two sums of forces we need are sum of forces horizontally, so we're going to represent that with a little x, and the sum of forces in the y direction, we'll represent that with a little y. So we've got sum of forces in x for horizontal, sum of forces in y for vertical. We'll tackle the horizontal first. So in order to do this, we're going to need to look at which of the forces on my diagram are going horizontally. There's two of them. You've got, let me highlight them for us, okay? That's going to be our horizontal. We've got the force of friction, we've got the force applied. Those are our two. So we're going to put those in our sum of forces in the x direction. But when we do, we have to consider their direction. Okay, so you've got some going in the positive, some going in the negative. Okay, so in the x direction, the one that we have that's positive is the FA. Okay, and to that we have to add the FF. But the FF is going in the negative direction, so it's plus negative force of friction, like so. Sum of forces in the x direction equals FA plus negative FF, which really boils down to FA minus FF. So that would be what you would get for your sum of forces in the x direction for this particular one. Now in the y direction, it's really similar. Got to move this up just a little bit. In the y direction, that's vertical. You want to look at all of your forces that are going vertically. So there's two of those. You've got your Fn and your Fg. I want you all to pause the video again, okay, and decide what you think the sum of forces in the y direction should be. Pause the video now and discuss. Okay, hopefully you all discussed what you think it is, and what you should have come out with, hopefully, is Fn, because Fn was going positive, plus negative Fg, because it was going down, which is really equal to Fn minus Fg. Okay, so that's your sum of forces in the x direction and in the y direction there for that. That's going to be your fourth step in your free body diagram. Now your last thing that you need to look at is decide if these are balanced or unbalanced. Balanced forces give no acceleration because everything basically cancels out. And what does no acceleration mean? It means constant velocity. Okay, so if it says constant velocity, that means there's no acceleration, which means balanced forces. The flip side of that is unbalanced forces mean there is acceleration. Okay, so unbalanced means there is acceleration, balanced means there's no acceleration. So let's go see if that is balanced or unbalanced in our diagram up here. Okay, so looking at our diagram, in the x direction, we've got an FA that's bigger than the FF. They're going opposite directions. Do you think it's balanced or no? Well, it's going to be unbalanced, and the reason for that is that our FA is bigger than our FF. Why did we make FA bigger than FF? We did it on purpose because the car accelerates. So in the x direction, it's unbalanced. You could think about it as tug of war, okay? FA versus FF, which one's going to win? Okay? It's unbalanced. FA is going to win, so it accelerates. And then in the y direction, our Fn and our Fg are exactly equal. And why did we make them that way? Because our car is just going to be going along the road, not falling into the road and not flying up because the road kicked it or something. So since it's not moving vertically, staying the same vertically, that's balanced. That's a constant zero velocity in the vertical direction. So you can see this in our picture. The x forces look unbalanced and the y forces look balanced. And you can also tell from the question, because it says we're accelerating, which is the unbalanced in the x direction, but with your common sense, you could think of y as balanced. Okay, so now what you're going to need to do is work on the practice. I'm going to leave a key to the practice with the sub, so you can ask the sub and check on that. And if you got any questions, you can email me and I'll be back next class to go over this and make sure everybody's got everything down. So you're going to be finishing that practice, and then the other thing you have to do is the PhET Forces Exploration in Google Classroom. Make sure you get working on that. It is due today. It shouldn't take you that long. You can work in groups, but every person needs to submit their own document for that. So make sure you get those in today. All right. I'll see you guys on Friday. Hope you'll have a great day. Miss you all. Love you all. Have a good one. Be nice to the sub.